Hey, I'm Alice FONTBONNE and I'm going to present you Formidable, a differential ray tracer with NURBS capabilities. Before introducing you to Formidable, I'm going to introduce you the context of the creation of Formidable, which is the new space applications. Nowadays, most applications need the best image quality, and in particular, quite obviously, for new space application, we need to pack as many functionalities as possible in the smallest volume possible. So we have to miniaturize the platforms and instruments into small volumes like a CubeSat in 1U, that means 10 centimeter by 10 centimeter by 10 centimeter, and that's very small. And we need also the best image quality. So we need the best image quality and compactness, and this means that we need freeform optics. Just for the following, I'm going to use this definition of the freeform optics. So a freeform surface is defined as a surface whose surface shape lacks translational or rotational symmetry about axis normal to the mean place. That means a surface like this one is not a freeform surface, nor an aspherical surface, nor a part of an aspherical surface. But this kind of surface with x-axial symmetry is a freeform surface. To design optical systems, and in particular optical systems with freeform surfaces, we can use commercial design software like Code5 or Zemax because they deliver results that we can trust. But in the same time, there are several drawbacks. For example, they are not free and they are ITAR. That means if the US government wants to restrict the access to Code5 or Zemax, it's possible. And furthermore, the core is not modifiable. That means if you want to add things to this software, it's quite complicated sometimes. About freeform optics, while new kind of freeform surfaces are available in commercial software, the feature sometimes comes at an extra additional cost. So if we want to use new freeform surfaces for breakthrough in optical design, we need another solution. And this solution is homemade optical design software. So I'm going to present you Formidable and why Formidable is so formidable through its features, from the less scientific one to the most scientific one, maybe. So the first one is the ESCL license. After there is a Python interface, the differentiability, the real ramming, the NURBS capabilities. And about the NURBS capabilities, I'm going to present you some results about the new optical performance improvements that we can obtain with such NURBS capabilities. So first, the ESCL license. So Formidable is under ESA Software Community License. That means if you want to download Formidable and you are part of one of these countries, you can just by scanning this QR code or using this URL. And if you want another argument to download it now, I will give you it now. The first one is interoperability. That means the Python interface. You can benefit from the power of a programming language, and if you are comfortable with Python, you can quite simply define and optimize an optical system. So I'm going to use one particular example to show you that. So the first step is the definition of the optical system with all classical specification of an optical system. So here you have the optical system in Formidable. You can define the object. It is in far field here. You can define the aperture, you can define the spectrum, and you can define the optical surfaces. After, the step 2 is the definition of the merit function, but I'm not going to speak about it now. And the step 3 is the optimization. Here you can see that you can quite easily optimize with one line of code your optical system, and in particular, if you are familiar with Python and in particular with SciPy, you can recognize the least squares function. So here you can see that you can use your favorite libraries with formidables. And here you can recognize the method, which is Levenberg-Marquardt, which is exactly the same method that is used in Code 5 or OpticsUlio to optimize the optical system. So you can use in Formidable the Levenberg-Marquardt optimization process. You can also use Python for all your custom plots or animation. For example, here I make fun creating a spot diagram as a function of the number of threads across the optical system. And in fact, you can use Python for all your custom applications that, for example, the application about computer-assisted design, so creating some code to convert your optical system in Formidable to your CAD tools, or in fact, whatever you want. The next feature, and a very important one, is the differentiability. The differentiability is the fact that the ray properties are calculated together with their derivatives as a function of the variables of the optical system. That means that for an example like this one, in general, you can, and for a particular ray, in general, in optical design software, you can quite easily have access to the intersection of the ray with the different surfaces. With Formidable, you have this information, and you have also access to the derivative as a function of things like the tilt of the mirror. And for example, if you tilt this mirror, you have the information on how these points will move with the tilt of the mirror. So if you have information on rays, you can have information on the merit function, and that can be quite nice for things like, for example, optimization. So I'm going to use this as an example. Traditionally, if you want to optimize a merit function here as a function of only one variable value, you have to calculate several points of the merit function here. And depending on your optimization algorithm, you will calculate them differently. Now, with Formidable, you have an information in addition, and this is a derivative. So you can easily guess the optimization landscape and quite easily obtain the best merit function value as a function of the variable value, depending on your optimization algorithm. So derivatives could be useful for several features, and in particular optimization and so on. The next important feature of Formidable is the ray aiming, and you can ask why ray aiming is so important, because we can find nowadays quite a lot of differential ray tracer on the internet, but they, in most of them, not have ray aiming. So ray aiming is important depending on what you want to do, and in particular, if you have a quite easy optical system with a stop before the optical system, ray aiming is not important. But if you have a complex optical system with a stop position inside the optical system, ray aiming is very important. Here is a first example without ray aiming. So you have the stop position here with the rays crossing the top and the bottom of the stop. And if you want to trace rays off axis, you will first determine the entrance pupil, and in particular the paraxial entrance pupil, which is this size here. And you will try to link your off-axis rays to the entrance pupil here. Now, if you trace the ray across the optical system, you have something like that, and you can see that the ray which is linked to the top of the entrance pupil is not linked to the top of the stop position, and this is a problem. And this is because the entrance pupil is not the paraxial entrance pupil, in fact. And this ray does not enter anymore. So you have a problem here. And ray aiming is the fact that a guess must be made to determine to determine how these rays will come through the optical system by passing by the stop here. And if you have ray-aiming, you can have something like this for these same off-axis rays. And you can do that for several field of views. If you want to know more about that, do not hesitate to save the date of Jean-Baptiste Vallatier's PhD defense, who is one of the creators of Formidable. So Formidable has real ray aiming by default. The next feature and last one, but not least, is the NURBS capabilities. NURBS is for non-uniform rational B-spline surfaces. And NURBS are a local representation of freeform surfaces, which is quite different of a global representation, which is the most natural and used nowadays. So here you have a global representation for a particular example of a conic, which is a sag here as a function of x. And if you want a freeform surface, you can use the xy polynomials, for example, and one coefficient like this one, and another coefficient like this one. And you can see that freeform coefficients impact all the surface. And in the same time, it impacts even this kind of part of the surface, which is not manufacturable anymore. On the contrary, a local representation does not modify all the surface. But the drawback is that for NURBS, it is not parameterized with x and y, but with different parameters. And the cycle is defined with an equation like this one, with a basis function and control points. So you have several control points, and these control points enable to define a surface, and each point has a local area of effect. That means if you move this point, you impact only one part of the surface here. Now with NURBS comes several difficulties, and in particular with the definition of the aperture. So first, in classical freeform or not system, the aperture can be defined quite easily. So here you have a surface which is moved like that, and you can quite easily, with a freeform surface defined with a global representation, define a reference sphere and a reference plane like this one. And with this reference plane, you can quite easily define an aperture and know if an incident ray goes through the aperture or not. So sag-defined surfaces enables an easy definition of aperture. It is a little bit more complex to define an aperture with NURBS. So Formidable decouples surface definition and aperture definition, defining a projected aperture. And it is possible with Formidable to re-aim with NURBS. And now that we have defined NURBS surfaces, the question is where to use these NURBS surfaces. Nowadays, freeform surfaces are necessary in off-axis telescopes to obtain good performance and compactness. And if you need freeform surfaces, I think that you can just try NURBS. So this part of the presentation is about Clément Frélier's work at the end of this PhD that will be presented on December the 5th. I will present results from sphere to freeform. That means a comparative study between NURBS and XY polynomials. And after, I will show you some results about the conversion from generic freeforms to NURBS and the results that we can obtain with that. For the first example, from sphere to freeform, I'm going to use this case study design of a 3-mirror anastigmat telescope. So here is the optimization starting point with the mirror 1, 2, and 3 here that are all spheres. And the stop is on the M2. Here are the specifications with a focal length of 100 millimeters, a field of view of 4 by 3 degrees, and a f number of 1.5. The goal is to compare the optimization of this starting point with using XY polynomials and using NURBS. But we will use XY polynomials in thematic and NURBS in Formidable. So the first question is how to properly compare the two results that we will obtain. To compare properly the two optimizations in the two software, the first goal is to have the same merit function. And inside the merit function, the first goal is to have the same pupil sampling. So here Clément used a pupil sampling, a rectangular pupil sampling. So here is the pupil and it's rectangular. And with Formidable, the pupil sampling is 21 by 21, which is odd. So here you can add the center of the pupil. And unfortunately, with Optic Studio, it's only even pupil sampling. So it's 20 by 20, and we check that 22 by 22 gives a similar results. So it's without the center of the pupil, but in fact it's quite the same. So pupil sampling is as similar as possible and sufficiently dense for freeform optimization. The next goal is to have the same field sampling. So the field is here or here in the sensor, and Clément used 5 by 5 field sampling, and field sampling is the same in Optic Studio and Formidable. And next, the next goal is to have the same goal in general and constraints. So the optimization criterion, which is a goal, is the transverse aberration, which is named a transverse aberration in Formidable, and the spot with TRCX and TRCY in Optic Studio. So here, for this optimization starting point, we have rays like that, and the goal is to have an optical system with at the diffraction limit or kind of. That means rays that course correctly on the center. We have to constrain the focal length using the central goal operands in Formidable and the sen X and sen Y in Optic Studio. And using this definition of a partial definition of the focal length with a shift ray, we can aim the rays for the 3 fields of views. And the next constraint is, and last constraint is the recurrence operands, which is named recurrence in Formidable, and we can use rag Y, rag X, rag B, and rag C in Optic Studio to do so. So the goal is here that a ray does not cross M2, for example, twice. So we constrain specific rays. So goal and constraints are quite the same in Optic Studio and Formidable. So if the question is it possible to optimize in similar way in 2 different softwares? The answer is yes, and we have a complete comparison here. So it is possible to compare NURBS and XY polynomial with a similar merit function. And we will do that with NURBS here and with XY polynomials in ANSYS. So first, we are going to define the variables of the optical system. So there are several tilts here in the optical system, and for the NURBS, we have several grid points for all the surfaces, and there is 6 by 6 control points with each time 4 degrees of freedom. And because we want that the surface presents symmetry along the x-axis, we have in fact only these control points that are used for the optimization. So with Formidable, nerves have 200 degrees of freedom. And now with xy polynomials, we use the coefficient of y2 as degrees of freedom, and the same for the degree 3 and the same of degrees 4, and these are only the only parameters that we use for the optimization, because also we want that the surface is symmetric along the x-axis. And we use that up to y5 and to y7 to compare xy polynomial of order 5 and xy polynomial of order 7, and in both cases the degrees of freedom are smaller than in the case of the nerves. So nerves need a larger degrees of freedom to be optimized, and the question is how long it takes. To answer this question about the computation time, here is a graph of the cumulative duration of the optimization as a function of the cycle number of optimization. And here you can see that the fastest is optimization with Zmax of xy polynomial of order 5, but Formidable and xy polynomial of order 7 is quite the same. So computation time is similar for nerves and xy polynomial of order 7. Now that we have checked that, the question is how many optimization cycles do we need to obtain the best result? And the answer comes with this graph. So as the mean RMS spot radius, so the average one, as a function of the optimization cycle number. And here, if we zoom in a little, we can see that in the 3 cases, there is kind of an asymptotic result, which is obtained for something like 60 optimization cycle number. So a similar number of optimization cycles lead to the best results. And about these results, you have seen that the Formidable nerves give the best result comparing to the xy polynomial of order 7 and those of order 5. And all these results, the mean RMS spot radius, is linked to a diffraction limit. With mirrors, which are achromatic, application depends on the diffraction limits. So for example, here you have the transmittance of the atmosphere, and with the xy polynomial of order 5, you have access to all these wavelengths of use for your optical system. But if you use the Formidable nerves, here you have access to this part of the spectrum in addition. So nerves pave the way for new multispectral applications. Now that we have compared the average results, we are going to compare the results across the field of view. So here are the nerves for the field of view along y and x, and here are the xy polynomial of order 5 and 7. And you have here the fact that for xy polynomial of order 5, the map is very uniform, but with a very large spot radii. And here, for the xy polynomial of order 7, the map is not uniform anymore, but in the same time, you have very good results there and there. Here, nerves give a more uniform and a better average result. And the question is it manufacturable? To check if it is manufacturable or not, we are going to check the freeform departure map. So here it is for the M1, mirror 1, and for the nerves and xy polynomial of order 5 and 7. And you can see here that mirror 1 nerves mirror is less freeform than xy polynomial of order 5 or 7. For the mirror 2 here, you have quite similar results, pick 2 value here for the nerves and for the xy polynomial of order 5 and 7. So M2's freeform departure maps have equivalent levels. And it's quite the same for the mirror 3. Okay, so to conclude this part of the presentation about the conversion from sphere, the optimization from spheres to freeform, with equivalent design strategy and merit function, we have similar computation times with Formidable and with xy polynomial of order 5 and 7. But we have also better results with nerves than with xy polynomials from spheres, because we have best average spot radius and we have better spot radius uniformity. That means that no compromise between the center and the edge of the field of view has to be made. And now we can ask, what if the starting point with spheres is not available, or what if you just want to improve one optical system with freeform? So this is the goal of the second part of the study, always from Clément Frey. So here I'm going to present you 2 case studies. The first is a freeform TMA with also the focal length of 100 mm and this specification. We use xy polynomial of order 5 here. And the second case study is a reimaging freeform TMA. So it's reimaging because you have a focal plane here, and there is an accessible pupil here. And the specifications are the following, with xy polynomial of order 7 for the representation of the freeform surfaces. The first thing to do is to convert from Optic Studio to Formidable. So here is a RMS spot radius field map in Optic Studio, and when we convert it to Formidable, it gives something like that. So here you can see that there are some reaming failures for the conversion, but it's quite okay, and retracing strategy is slightly different, but topology is similar. Now the next step is the conversion to nerves. So we depart from the xy polynomial of order 5 and we obtain things like that. There are some conversion artifacts, but with the optimization they go away, and we obtain something like that we can compare to the first map here. So here you can see with optimization of nerves there is 8% of amelioration of the RMS spot radii. If we now check the manufacturability of the mirrors, we depart from this mirror for the mirror 1 freeform with xy polynomial of order 5, and we obtain something like that. So it's there is an important peak to valley, but it's put in particular here or here and here, but it's kind of possible to manufacture normally this kind of mirror. It's the same for the mirror 2 and for the mirror 3. So freeform departure maps are reasonable normally for manufacturing. About the second results, so not the freeform TMA, but the reimaging TMA. Here with the polynomial of order 7, we have a map like this at the beginning, and doing the same conversion into nerves, we obtain something like that with the same color bar here and here. And this time we have a 66% of amelioration on the RMS spot radii, and this is very nice. About the manufacturability, we have results like these ones. So here are the mirrors with xy polynomials of order 7 for the representation, and here are the representation for the nerve surfaces. and freeform departure are reasonable too for manufacturing, except maybe this one, it could be a little bit difficult to manufacture, but we have to try. Okay, so to conclude, nerve surfaces enable to improve freeform optical systems in terms of spot radius size and uniformity across the field of view. Mirror shapes seems manufacturable, but we can ask what impact does the optimization starting point have on the optimization of freeform surfaces. And the next part of the conclusion is that similar results can be obtained with other optical path configuration, like this kind of optical path configuration, for example. So thank you for your attention. And here are some links if you are interested in Formidable or NURBS. Bye.